Good morning. Hope you are doing well. We will address today a topic related to methods. The topic is about recursion. Let me first recall what we did so far. Last time we were talking about the concept of methods. The main idea is that whenever we are having a problem, usually the problems are big. And that's why what we want actually to do is we want to solve the problem just by dividing it into sub-problems. And last but not least, for every sub-problem, we will implement a method. And at the end, we will conquer this method to solve the problem itself. And this has a lot of advantages. One of them is the code will be more understandable. It's clear whenever a problem occurs, whenever there is a bug in the code, we will be able to find it faster, since actually you are not having something we call spaghetti code, monolithic code, where you have to search in one single method where the problem is. But since actually we are dividing our problem into sub-problems, then most probably the problem, let's say, lies in a specific part of, let's say, the whole program. And that's why we will go to this part and then fix it. Now, again, methods work as follows. You have to consider it as just actually a box. Okay, this box will take some of the arguments, either 0 or more. And last but not least, the method actually returns a value. The value is either something that will be returned, it's optional. Then we have to know the data type of the value that will be returned. But if the method is not returning anything, then actually the method should be a void method. Okay, now let's go back and let's think about let's say an algorithm that we have already implemented before, and we implemented it often. We implemented it once in the main method, and last time we implemented a method to solve it. Okay, now the problem is the factorial one. That's what I want actually to do is, I want actually to calculate the factorial of a number x, knowing, or n, knowing that the factorial of n corresponds to 1 times 2 times 3 till you reach n in this case. Thus, I know exactly that the signature of the method will be a method that returns an integer as output. It's called factorial. I will just actually call it ITE. I will tell you exactly the meaning of it in a few minutes. And last but not least, the method will expect as an input an integer in this case. Now, it's a clear counter loop that we have to implement, starting by a counter which is equal to 1 till I reach I, which is equal to the n. I have to perform some task. Whenever my I reaches n plus 1, I have to stop. And what do I have to do? I have actually to calculate a result, which is the factorial, where the value of the result will be always updated by multiplying actually the result by I. And the initial value of R is equal to 1 in this case. Okay, nice. It looks really good. Now what we need actually to do is we need only to return, let's say, the result, since actually the method is having as a return data type an integer in this case. Okay, now I have already prepared, let's say, the main method just to test it. Now I will be expecting an input from the user, and last but not least, what I will do is I will call the factorial of this number, okay, x, and last but not least, I want actually to print it. Thus, I will compile. The code must probably compile correctly, and now no, it doesn't. That means there is a small problem that we have to fix. It's called factorial iteration. Okay, thus let me stop it and let me compile. Okay, thus now most probably the algorithm will compile correctly, and now once I will run it, if I input 5, then I will be expecting 120 as a result, and what we get here is we get 120. Okay, and it works perfectly. If I do it, let's say, for in a number which is 7, then you have to get as a result 1 times 2 times 3 times 4 times 5 times 6 times 7, which corresponds to 5040 in this case. Okay, and last but not least, once I will do it for n equal or for value equal to 0, then the result should be equal to 1, and you get as a result 1 in this case. Okay, the method that we are implementing here is an iterative method. Okay, and once we talk about iteration, okay, you have always actually to think about, let's say, the constructs that we saw before in iteration, which corresponds to the for loop, the while loop, or the do while loop. Thus, you are having actually the following problem. What I want actually to do is I have a result. The result will be updated every time just by multiplying the result by a counter, starting by 1, till actually the counter reaches n plus 1, and then I have to stop in this case. Thus, this is, let's say, how we can describe, let's say, this problem. Okay, now let me comment actually this one, and let's think about actually the 5 factorial. Okay, now 5 factorial is equal to 1 times 2 times 3, okay, times 4. Okay, and last but not least, times 5. Now, once we have that, okay, it's clear that the 5 factorial is, let's say, the multiplication from 1 till 5. Now, I want actually to ask you the following question. What is 1 times 2 times 3 times 4? Okay, now, everyone actually will see that the 5 factorial corresponds in this case to the 4 factorial, which is exactly what we are having here. Okay, because 4 factorial is 1 times 2 times 3 times 4 times 5. And last but not least, actually, what I will be having here is actually times 5. Now, we want actually to generalize the problem itself. That means the x factorial will be equal to 1 times 2 times 3. Okay? And then times, I will write actually few dots, and last but not least times x minus 1. And the last one is times x. And then I will tell you the following. If you take a look at x factorial, okay, then the x factorial is equal to 1 times 2 times 3 times x minus 1. And this one actually corresponds to x minus 1, and the whole thing actually factorial in this case. Okay, thus you see that the definition now is not an iterative definition, but actually in math we call it a recursive definition in this case. Okay, thus let's start actually to think about the implementation of, let's say, this method. Okay, now we will be writing a method with the same signature. It returns an integer. Now it's called factorial of, let's say, something. However, the factorial is a recursive method in this case. Okay, now I will just start actually to tell you the following. Okay, once we talk about recursion, the first thing is we have to think about something called the anchor case, the base case. The anchor case is the case that I have to reach once, just actually to stop the execution of the method, which is the recursive method in this case. Now, almost every method, which is actually a recursive one, okay, will consist of two parts. One part is the anchor case, the base case. Okay, usually if we don't have an anchor case, you will see it later. If we will remove it, actually what will happen in this case, actually the program will never terminate. Okay, thus my anchor case actually for recursion is if once actually I reach n, which is equal to 0. Thus, if n is equal to 0, I know exactly that the factorial of 0 will be equal to 1. Now, I don't need an else part, but what I will do is I will return now right away, let's say the recursive one, which is x minus 1 factorial times x. Since I'm using n here, okay, I will be calling factorial rack of n minus 1. Okay, and last but not least, times n. Okay, now once you take a look at this definition, okay, this definition in this case is a definition which is a recursive one. What does it mean, recursive? It means that I am defining a method, and in the body of the method, I am using, I call the method again. This is actually a recursive one. Okay, now this is called the static view of recursion, meaning we will see whether, let's say, Java will be able to handle it. Now, if you take a look at this one, and I will be calling, instead of the factorial iterative with factor recursive, okay, I will just replace the ITE by rec. We see exactly what kind of result we will have. Small problem, semicolon is missing, no problem. We will just go fix it. We run it again. And now what we will be getting here is I have to enter a number. The number is 5. Okay. And I should get 120 as a result. And then I think we get actually 120 as a result. Okay, thus the question is, how did that work? Okay, I will tell you exactly how the whole thing actually did work. Now, look, if I will call factorial rack, this is, let's say, the tracing, this is the dynamic view, how the whole thing actually will work. If I call factorial rack of 5, what Java will do is, we'll go and check, is 5 equal to 0, yes or no? It's not, I will not return 1, but what I will be returning here is factorial of rack of n minus 1, which corresponds to 4 times 5. Okay, thus, what Java will see here is, it sees now a kind of a call that cannot be evaluated. Why? Because in order to calculate the value of 5 times factorial rack of 4, first of all, I have to compute the factorial rack of 4. This is exactly what recursion is. Java will go and see in my file, do I have a method which is called factorial recursive that takes as a parameter an integer, yes or no? Yes, I will find one, and the same method will be called again. Now, the question is 4 equal to 0, yes or no? It's not, I will not return 1, but instead of having a factorial of 4, I have to compute now the factorial rack of 3, which is 4 minus 1, times 4, and last but not least, the multiplication times 5 will remain. Okay, now, nice. What I will do is, I will go further. Here, Java will see the same factorial rack of 3 times 4 times 5. Just to be able to evaluate the whole expression, first of all, I have to evaluate the factorial rack of 3. Java will look whether there is a method called factorial rack. In this case, that takes as a parameter an integer. It finds the same one. This is recursion. And what will happen in this case, Java checks 3 is not equal to 0, and that's why the factorial rack of 3 will be replaced by factorial rack of 2 times 3. And last but not least, times 4 times 5 will remain, and the evaluation will be postponed actually for a while. And the whole thing will go further. Factorial rack of 2. Okay, 2 is not equal to 0, but 2, okay, in this case is different than 0, and that's why I will go and calculate the factorial of rack of 1 times 2 times 3 times 4 and times 5. Okay, now last but not least, I will go and calculate the factorial rack of 1. Factorial rack of 1 is equal to factorial rack of 0, okay, times 1 times 2 times 3 times 4 and times 5 in this case. Now, look, now what will happen is the following. Factorial rack of 0. Java will go and check, do I have a method called factorial rack that takes as a parameter an integer, yes or no? It's the same one. It will call the method. Now the anchor case is needed in order actually to stop. Thus what I will be getting here is the factorial rack of 0 will be replaced by 1 times 1 times 2 times 3 times 4 times 5, and last but not least, this one, I do not have a recursive call anymore. I have now a kind of multiplication of integers. Java will return 120, and this will be actually the result in this case. Now, what you see here is the dynamic view of recursion. Okay, nice, it's easy, simple. Okay, and the nice thing is the whole thing is declarative. Okay, now look what will happen in this case if someone will forget the recursive, the base case, the anchor case. Now, once I will do it, okay, and I will just actually run it with the 5. Now, what will happen in this case? Java will go and calculate factorial rack of 4 times 5, factorial rack of 3 times 4 times 4 times 5, and then factorial rack of 2, then factorial rack of 1, then factorial rack of 0, and there is no anchor case. Thus, I will go to factorial rack of -1, -2, -3, and the whole thing actually will never stop. In this case, you will see a call of a method, which is a method that will never terminate. It's a non-terminating method. One day, the compiler will detect it that actually this method will never actually terminate, and you will stop the execution here in this case. Okay, thus this is let's say how recursion works. Thus usually what you need here is an anchor case to stop the execution. And the most important thing is this approach, we call it a declarative approach, because actually what I'm defining here is I'm not defining how Java will execute the whole program in order to calculate the factorial of a number, but I'm saying if you want actually to have the factorial of a number, then if the number is equal to 0, okay, then the factorial of this number is 1. This is my base case. Otherwise, give me the factorial of n minus 1, then I can get you the factorial of n just by multiplying the value of the factorial of n minus 1 times n. And you will see that every time I will be describing a method or a problem recursively, I will never use the keyword until. Because if you talk about until, in this case, you are having iteration. Okay, thus look, if I have, let's say, a for loop and I want, let's say, to describe it in English, I would say the following: to calculate the factorial of a number, I have to have a result. A result is equal to 1 in the beginning, and I have to update the result just by multiplying every time this result by a counter that I have to increment until this counter reaches n plus 1, and then I will stop. Now, once you talk about a recursive one, we don't have actually this statement until anymore. Okay, the whole method will consist of two parts. The first part is the base case that will let me actually stop the execution of the whole code. And last but not least, the second actually part is the recursive call. Okay, and I will never actually talk about, let's say, I will never actually use in the description of a method which is recursive and until one. Okay, now let's go further and let's implement a method. Okay, the method that we want to implement is a void one, and what it does is it's just actually does a countdown. Okay, that means it counts down from let's say a number n till 0. Okay, now the question is what will I do? Okay, I will just implement it recursively. Okay, I know exactly how the whole thing can be implemented recursively, but now what I will do is I will just actually write the following. If you want actually to count down, my base case, it's clear whenever I reach 0 in this case, because if I reach 0, what I will do is I will write system.out.println. Okay, and in this case I will be printing 0 as a value, or n, it's actually the same thing. Okay, now else what I will be having here is system.out.println. Okay, what I will be printing here is the n. Okay, however, the second actually part of the else part should be a countdown in this case, okay, in order to count down, not starting now from n, but starting from n minus 1. Okay, thus you see an else part consisting of two parts, and that's why what I will do is I will put them into a block of statements. Thus, the if part will give me now the anchor case. Okay, whenever my n will be equal to 0, I will be printing a 0. This is it. However, if the number is not equal to 0, then I will print it, and I will go and count down from, let's say, the number minus 1. That's if I'm having 5. 5 is not equal to 0, then I will be printing 5. And next time I will go and start the countdown, not from 5, but from 4. The countdown from 4 will call itself recursively. And what will happen in this case? 4 is not equal to 0, I will be printing the 4. And once I printed actually the 4, I have to count down starting by the number 4 minus 1, which is 3. Now the nice thing is, once I will go and let's say call the method here, which is the countdown x, okay, and in this case, if I will compile, we don't have any syntax error, then this one will work correctly. If I will run, and I will be expecting, let's say here, if I enter 10, I will be expecting, let's say, a countdown from, in this case, from 10 to 0 in this case. Okay, it's nice, it's simple, and the recursion, you see it here, easily because you are implementing a method, and inside the method you are actually having a call, okay, that uses the same name of the method. And in this case we are talking about a recursive method. A method that is recursive is a method that calls itself. Is this part clear for everyone? Or I hope that actually this part is clear from everyone. If this is actually the case, we want, let's say, to go further to think about a problem which was discussed a lot in math a few years ago. Okay, now the problem is called the Fibonacci problem. Let me give you the definition of it. And after that, we will think about how actually the whole thing will be implemented. Okay, now let's go further to, let's say, the Fibonacci problem. Okay, now it's a farmer problem. Fibonacci is an Italian mathematician who was actually the first one to solve actually this problem. Okay, the problem is a simple one. We start actually with a female rabbit, and we have actually some constraints. Okay, the first constraint is that a female rabbit matures after 2 months. Okay, now, and the second actually thing is we know that we will be starting with one rabbit. Okay, and the rabbit is a female one, and we want actually to calculate the total number of rabbits we have every month. Okay, yes, keeping in mind that actually the rabbit will always be able to deliver a new rabbit, which will be always a female. Okay, now this is an additional constraint. Okay, however, a female rabbit can only be able to deliver babies whenever actually she reaches actually 2 months. Thus, the question is, we would love actually to know how many rabbits will we have actually in total. Okay, this is actually the Fibonacci problem. Now, let me think about actually month 1. I want you to tell me in month 1 how many rabbits do we have. Okay, thus, if you think about actually the following, we start only with one rabbit, which is a female one. And the constraint is that the rabbit cannot deliver unless actually she becomes mature. And the second actually, let's say, constraint is whenever a mature rabbit will deliver, then actually the baby will be a female one. Thus, if I will go actually to month 1, then actually the total number of rabbits will be 1 in this case. Okay, now in month 2, the total number of rabbits is still 1 because actually the rabbit is not mature enough. Now, once we go to month 3, okay, then I know exactly that in month 2 the rabbit actually is mature. That means in total we will be having 2 rabbits, and the 2 rabbits are the mom, the female rabbit, which is actually mature, and the second one is, let's say, the rabbit, the child in this case, who is a female. Okay, now let's go actually to month 4. Now the question is, how many rabbits will I have in month 4? Okay, as we know, rabbits are really productive. That means the mom will get a new baby. The baby, the first baby of the mom, is still young actually to deliver. And that's why in total, I will be having exactly 3 rabbits. Okay, now we will go actually to month 5. And we want actually to know exactly how many rabbits we have. Okay, now we are having 3 rabbits. All of them are females. We have the mom and actually 2 kids. The mom will deliver a new baby. And the first baby is now mature, and this one actually will deliver a baby too. That means in total we will be having 5 rabbits. Okay, now if we go to month 6, the question is, how many rabbits will we have? And if you think about it, it's actually the same. We are having 5 rabbits in total. The mom will deliver a new baby. Okay, that means we have 5 plus 1. Now the first child, okay, is mature, was mature, delivered actually once, he will deliver a second time. This is actually the second one. Now the second baby becomes actually mature and delivers 1. And the last one is still actually young, and that's why it doesn't deliver anything. And that's why the total number of rabbits will be 8. And now, if we go further, now everyone actually will see, let's say, the chain. If I am having actually month 7, then I know exactly in total that the total number of rabbits will be and someone actually most probably will tell me 13. In month 8, I will be having 21. In month 9, I will be having, in this case, 34. The question is, how is this number coming? This number is coming from the two previous actually numbers of rabbits. I will add them and you get actually 34. If you get 1 plus 1, then you are actually getting in month 3 is 2. If you are having 2 plus 3, then in this case you get 5. Okay, 3 plus 5 you will get 8. 8 plus 3 you will get 11 and so on, 21 and so on. Okay, and that's why the question is, how can I define the factorial 1? Okay, now I know exactly factorial of 1 is equal to factorial of 2 is equal to 1. Okay, this is actually the base case. However, if you tell me what will be the factorial of n, I will tell you the total number of rabbits in month n corresponds to the total number of rabbits in month n minus 1 plus the total number of rabbits in n minus 2. Okay, thus, once we have that, now we have actually the definition, and what we need to do is this mathematical definition has to be implemented in Java. Thus, I will be implementing a method. The method is something that will return an integer. It's called, let's say, Fibonacci. Okay, it's not factorial, I'm sorry. It's actually Fibonacci. I will call it fib, and then fib, and last but not least, fib and fib. Okay, this is the Fibonacci one. Thus, the Fibonacci one will take as a parameter n. Okay, and I will write actually the following. Wallahi, if n is equal to 0 or n is equal to 1, then I know exactly that the value, or I will start actually with month 1. Okay, and n is equal to 2, then in this case I will be returning 1 as a result. Okay, otherwise what I will do is I will take actually the recursive call, which is the Fibonacci of n minus 1, okay, plus the Fibonacci of n minus 2 in this case. Okay, now it's nice, it's good. Now what we will do is we will just actually calculate the factorial of x. Thus I will write system.out.println, and what I will have here is the Fibonacci of x in this case. Okay, now once I will go, if I will compile, then hopefully everything will compile correctly. Okay, and once I will run it actually with 6, I should get 8 as a result, and you get 8. Now, if you will run it with 8, okay, I should expect 21, and you get actually 31. Now, if you go to 9, I'm expecting 34. And what you will get here is you will get actually 34 as a result, which corresponds actually exactly to what, let's say the series that we had actually here in month 9, we are having actually 34. Okay, for sure, some people actually want to start with month 0 and month 1. This could be actually the case because in month 0, if I'm having only 1 rabbit, and in month 1, actually the rabbit is still young, okay, then in this case, okay, the result, let's say, will be shifted a little bit. However, actually the way how the whole thing will be executed will be the same. Okay, now let's go actually to Fibonacci of a large number, just actually to see how the whole thing will work actually dynamically. If I do it actually for Fibonacci of 100, I will be having actually a small problem. And the problem is not that actually the program will not terminate, but once we go and to see, let's say, the dynamic view of the execution, we will be able actually to understand it better. Okay, and that's why let's go and see how the whole thing will be, let's say, executed. Okay, now this is actually the dynamic view of the function. I will be having Fibonacci of 5. Fibonacci of 5, I will check. 5 is not equal to 1. And 5 is not equal to 2. And that's why I will go and return Fibonacci of 4 plus Fibonacci of 3. Okay, thus, this is actually the call Fibonacci of 4 plus Fibonacci of 3. Now, once I will go actually to get the Fibonacci of 4, I will just actually focus on this one. El Fibonacci of 4 is in this case equal to Fibonacci of 3 plus Fibonacci of 2. Why? Because the 4 is not equal to 1 nor equal to 2. Now if I have the Fibonacci of 3, then the Fibonacci of 3 is equal to the Fibonacci of 2 plus Fibonacci of 1. Since now n is equal to 2, okay, the Fibonacci of 2 will return 1. Now the question is, I still have actually to execute the Fibonacci of 1. Fibonacci of 1, according to this definition, will return 1. And that's why here, once I will return 1, I will actually, let's say, propagate back the value to it. I will be having here 1 coming from n equal to 2 from n equal to 1. That means Fibonacci of 2 plus Fibonacci of 1 will be equal to 2 in this case. This one actually will be propagated back for the Fibonacci of 3, but I have to execute the Fibonacci of 2 for a second time. Fibonacci of 2, since n is equal to 2, I will return 1. And now I will be having 2 plus 1, and the Fibonacci of 3 plus Fibonacci of 2 will propagate back the value 3. Okay, this is the value of Fibonacci of 4. Now, Fibonacci of 3 has to be executed the same way. This will be executed in the right part of the tree. Fibonacci of 3, 3 is not equal to 1, 3 is not equal to 2, and that's why the Fibonacci of 3 corresponds to Fibonacci of 2 plus Fibonacci of 1. Fibonacci of 2 is returning 1, while Fibonacci of 1 is returning 1. Once you propagate it back, you will be having 1 plus 1 is equal to 2, and you propagate here the 2 back. Now, here we calculated the Fibonacci of 4, which is 3, and the Fibonacci of 3, which is equal to 2. 3 plus 2 will be equal to 5, and this will be the return value that will return in this case. Now, I will tell you exactly what the main problem of this type of definition if you do it recursively. If I would have had Fibonacci of 100, then the Fibonacci of 100 will be equal to Fibonacci of 99 plus Fibonacci of 98. The Fibonacci of 99, to execute it, I have to execute Fibonacci of 98 plus Fibonacci of 97. And once I execute Fibonacci of 98, I have to execute it again. And that's why the 98 will be executed twice. And to execute Fibonacci of 98, I have to execute Fibonacci of 97. And to execute Fibonacci of 98 here, I have to execute Fibonacci of 97 again. And the Fibonacci of 99 is equal to Fibonacci of 98 plus Fibonacci of 97. Thus, you will keep on executing and re-executing the calls, although we have already done them before. It's like here, Fibonacci of 3 has been already calculated here. What I have to do is, once I will do it, I have to calculate it again. Okay, why? Because I'm not memorizing, let's say, the values that have been already computed in the previous months. Okay, now this is, let's say, one small problem that can be solved easily. Okay, however, here you see that even now the whole Fibonacci didn't actually stop yet. Why? Because actually you will be going into a branching of a lot of calls, and this will need a lot of time actually to get executed. However, actually, if I will do it with, let's say, a number which is not that large, if I do it actually with Fibonacci of 10, then after a few seconds you will get actually the result. In this case, if I will do it for Fibonacci of 20, okay, after a few seconds you get actually, let's say, the result, but whenever the number will become actually bigger, then in this case we will lose track, and the tree actually will become huge, and we will need actually to wait long actually to do it. Now, there is actually a technique to solve actually this problem, which is part of something called dynamic programming, that if you will join MET, then actually most probably will be getting, let's say, a topic, a lecture about it. Okay, nice. Let's go further. Now, we did nice things related to dealing with integers, just actually to perform some of the operations recursively. And now what I want actually to do is, I want to have a string CSEN, and what I want to do is, I want to reverse it, NESC. Okay, the question is, how can I do it? Okay, now, iteratively, it's a simple one. Okay, we have already implemented last time, but what we want actually to do is, we want actually to think about a way just to define, let's say, reverse in a recursive way. Okay, that's what I want to do is, I want actually to reverse CSEN. Okay, this is what I want actually to do. Okay. Okay, now if you want to reverse CSEN, then what you can do is you can actually do it in two different ways. Okay, you can get the C. Okay, this one you can get it easily. If the string is not empty, then I know exactly it has at least actually one character. I get actually the first one. And what I have to do is I have to concatenate this C, okay, to the result of reverse of SEN. Because the reverse of SEN is, in this case, okay, NES. And once you will concatenate it to the C, you get actually this one. Okay, and this is exactly, let's say, how you could reverse recursively a string in this case. Thus, the reverse of the string could be implemented as follows. Okay, if the string is empty, then the reverse of a string is an empty string. This is actually our base case, and we need it. If the string is not empty, then it has at least one character. Okay, I will take actually the first character. I will take it and concatenate it backwards to the reverse of the string without actually the first character in this case. Now the only question is how could we do it? Now I will replace this one by a string. This one is a next line, and last but not least, this one will be a string that will be input in this case, string S. Okay, thus I will keep this one in order to post it on the MET website, and you can actually play a little bit around with it after taking a look at the lecture. Now what I want actually to do is I want actually to call the reverse of S in this case. But first of all, I have to implement it. Okay, thus let's go further and implement a method which is a static one. The method will return a string. It's called reverse. It takes as a parameter a string in this case. Now, I will do it recursively. Now, if the string is empty, okay, now how can you check that the string is empty? Okay, you do it with the length. If the length of the string is equal to 0, I know exactly at the end of the day the string is empty. I will return it in this case. Otherwise, what I will do is I will return actually the string, okay, after reversing, let's say, this string without the first character. And we saw it actually already in previous lectures. There is actually a method called substring, okay, of 1, meaning I will be removing actually the first character. And last but not least, I will concatenate the whole thing with char at of, which is the character in position 0, the first actually character in this case. Okay, thus let's see how this one will work. I will do it. I will compile. And what will happen in this case, once you have, let's say, the running of the call with the reverse of a string, okay, we will do it with CSEN, okay, and what you get as a result is NESC, okay. Thus, here what we did is the substring is a predefined method that gives you this string without actually the first character, okay. Is this part clear for everyone? Again, if you go back to, let's say, the definition, or let's say this simulation actually by hand, we said if you really want to have the reverse of CSEN, okay, this will be actually the result, then please reverse the string without the first character. Okay, if the string is not empty, then there is a first character. And what you do is you concatenate, let's say, this character backwards to the result of reversing SEN in this case. This is exactly what we see here. Now, some people will tell me, I can do it differently. If I want actually to reverse a string, I will call it reverse to CSEN. Okay, it should give me actually the same result, which is NESC in this case. Now, how can I do it? Okay, instead of taking the first character, I will take actually the last character, and the last character is N. Okay, because if a string is not empty, then it has at least one character. This character can be either the first or the last one. Thus, I will actually be getting the last character in this case. And what I will do is I will take, let's say, the reverse. Okay, 2, and I will reverse the string without the last character, which is in this case the SCE in this case. Okay, because the N, if I have CSEN, the N should be the first character, and then I will take the CSE and I will reverse it. Once I reverse the CSE, it will be ESC, and if you concatenate the N to it, you will actually get in this case. Now, the only question is if I am having a string, I know exactly how to get a string without the first character. But if I have to get the string without the last character, okay, is there actually something that will help me to do that? I will tell you yes, there is a second predefined method in Java which is called Substring2. However, it takes two parameters. I will actually show you this one. Now, s dot substring of 0, okay, s dot length minus 1. Okay, now let me do it actually like that with 0 and s dot length. If I have actually this one and I want actually to let's say run it with CSEN, then in this case you get actually just an echo. Thus, a 0 meaning I will start from the first character. Okay, and last but not least, s dot length means it's exclusive. The last character that I will get is s dot length minus 1. Okay, look, if I will have 1 and then here, for example, till s dot length, then in this case I will be getting, let's say, the string without only the first character, but I will get actually all characters. Okay, in this case, if I do it with CSEN, the only thing that will be removed is the C. Okay, and what remains is the SEN. Now, if I want actually to do it, let's say now with the whole string without the last character, okay, then I will start with, let's say, the character 0. However, I have to stop by s dot length minus 2, and that's why, since actually it's in this case the second actually parameter is exclusive, I have actually to do it with s dot length minus 1 in this case. Okay, and this will help me to implement the recursive methods reverse, okay, where you will be taking the characters backwards rather than actually taking them forwards. Now, if I have CSEN, the result will be in this case CSE, and this is exactly what I want actually to get in this case. Okay, thus, this is the reverse too, and we will implement it together. It's actually almost the same one as this one. Okay, thus, I will just actually get it. However, this one will be called reverse 2. Okay, the anchor case is the same. Okay, and the only thing that will change here is the recursive one. Okay, now we said we get the last character. The last character is in which position? It's in position s dot length minus 1. Okay, thus you get s dot char at of s dot length minus 1. This is actually the last character of the string. And last but not least, I will call reverse 2 of the whole string without, in this case, the last character. This is s dot substring, where I will be starting always by 0. Okay, I will start by 0, and I will stop by s dot length, in this case, minus 1. Okay, thus once we have that, I will go, and I will just actually get, in this case, let's say the system.out.println instead of reverse. Now I will do it with reverse 2. Okay, thus I will compile. If we didn't actually forget any semicolons, then this one will compile correctly. Once I will run, if I will do it with CSEN, in this case, the result will be NESC, okay? And if you will do it, let's say, with any other string, okay, since actually I am entering here a line, okay, if I will do it with hello world, then the whole thing will be, let's say, reverse, starting actually from D till you reach actually the H in this case. Okay, thus the reverse has been implemented here now recursively in two different ways. The first way is just to take the characters back forwards, and you have to concatenate them backwards. or you take the characters backwards and you have to concatenate them, in this case actually in the front of the string. Both of them actually will give me the correct result in this case. Okay, now let's go to a more complicated one. Okay. No, it's not a complicated one. It's a simple one. I have a number. Okay, the number is, for example, 6. Okay, and what I want actually to do is I want to calculate the binary representation of 6. Okay, keeping in mind if I will do it with, let's say, 8, the result should be 1, 0, 0, 0 in this case. If I will do it with 11, or let's say 12, 12 corresponds to 8 plus 4. Okay, you don't have, let's say, a 2 and you don't have a 0, it should be 1, 1, 0, 0 in this case. Okay, now the question is, I want actually to write a method which is called binary. It takes a number, and what it does is it just gets, let's say, the representation of the number in binary. Okay, now let's go actually to think about actually the problem itself. Okay, now if I am having a binary number, what I need to do is I need actually to get the number and divide it actually by 2. This is actually how the binary representation works. Now, if you remember what we did in CSEN202, so on the binary representation, you will be having a number, you divide it by 2, you get a result. Okay, if the result is equal to 0, you stop. If the result is not equal to 0, you get the remainder. And after that, what you have to do is you have to collect the remainder from bottom to top. And that's why if you have 6 divided by 2, the result will be equal to 3, and the remainder is equal to 0. Okay, thus what I will do is, okay, I will go and know exactly in this case that I have the 3, and what I need to do is I need actually to get its binary representation, because actually the 0 I got it already. This is actually the 0, and what remained here is, okay, the result is 3. Thus what I will do is I will take actually the 3 and do the same actually for it. I get actually the binary representation of 3. The binary representation of 3 is 11 or 1, 1. Thus in this case I know exactly that the binary representation of 6, okay, corresponds actually to, I will write it in a sloppy way. In the implementation, we have to know how actually to implement it. The binary representation of 3, and I will concatenate actually to it, let's say the remainder, which is actually 0. Okay, if I have the possibility to call the binary of 3 and then concatenate actually to it the 0, then actually I will be getting the correct result. And that's why let's try actually to implement it. It's a method. The method is a static one. It's a void one. And it's called actually binary of a number, and the number is n. Okay. Now, I will do it only for numbers that are, let's say, positive and strictly greater than 0. Okay, that's if n is equal to 0, what I will be doing here is I will return. Okay, I will not do anything. And return, okay, although the method is a void one, I can return. The return is an abort actually from the execution of the method in this case. Okay, else I will be having actually 2 things to do. Okay, the number is not equal to 0. That's what I will do is I will calculate the binary representation of the number divided by 2. Okay, thus I will be calling binary of n divided by 2. And the second thing is I will write system.out.print. Okay, and what I will be printing here is that n modulus 2 in this case. Okay. Now, please take a look at this one. This is, let's say, the order here is a crucial one. We will go actually later in the tracing, and you will see exactly what I mean with, let's say, an order which is crucial in this case. If you would change it, then actually most probably the result will be totally, let's say, different in this case. Now, I will be getting a number. Okay, now I will change this one into next int. Okay, this one, instead of having it to be a string, it will be an integer. Okay, and last but not least, I will call binary of 12. Okay, now once I will compile and run it, I will be expecting 1100 as a result. What I'm getting here is a problem. Okay, just actually in this one. Okay, sorry about it. However, actually now once I will call the binary of x, okay, it's 12. Then in this case you will be getting 1100 in this case. Okay, and you can actually see it. Okay, it works perfectly. If I do it with 8, the result should be 1000, and 8 you will be getting 1000 as a result. And last but not least, if I will have it with for example 15, okay, 15 I should get as a result 1111, and you will be getting as a result 1111. Okay, this one actually works perfectly. Okay, now anyone who will try actually to do the following, okay, just to print the modulus before actually the binary, okay, the order will give you a totally different actually result in this case, and I will trace it in a few seconds. Okay, now let's go and take a look at let's say the representation of the binary representation of 12. Okay, 12 corresponds to 8 plus 4, okay, meaning in 2 of the power of 3 I should have 1, in 2 of the power of 2 I should have 1, however in 2 of the power of 1 as well as in 2 of the power of 0 I should have a 0 in this case, that the result should be 1100. Now once you do it, you get actually as a result 0011. That's actually the whole thing was actually reverse. Now the question is, why that? Let me trace it. I will return it actually back, and I will tell you exactly how the tracing of let's say recursive method actually could happen. Now look, once I will return it back, okay, and you will do it with 12, the result will be correct. Okay, now how does it work? Please focus with me. There are actually different ways how the tracing will be done. I will try actually to do it. Usually I do it on the board, but I will try actually to do it here on, let's say, a representation of a binary of 6. Okay, now you go and you check binary of 6 is 6 equal to 0, yes or no? Now it's not, and that's why I will go to the else part. Okay, thus this one will be capped actually into a stack. Okay, and the stack actually you have to look at it as a pile of things that I can only access the one on top. Now once I have actually the binary of 6, I will take it actually from the stack and I will execute it. 6 is not equal to 0, and that's why in this case what will happen here is I will be just actually going to the recursive call. Okay, now the recursive call will have actually the following. Okay, it will have, let's say, 2 calls. One of them is called binary of n divided by 2, which corresponds actually to 3. Okay, and underneath this one is a system.out.println, in this case of n modulus 2, which is equal to 0. Okay, now please actually take a look at the stack. The stack here will consist of 2 calls. However, if I am having a stack, okay, Java will go and get only the first one, which is the binary of 3. Okay, and the system.out.println will remain there. Okay, and that's why what will happen in this case, after getting the binary of 3, I will do it now in a kind of animation. I will get the binary of 3, and this is the one that I want to execute. The binary of 3, if you go back, let's say, to our definition, 3 is not equal to 0, and that's why what I will do is I will have 2 calls. The first call is the binary of 3 divided by 1. It's binary of 1. 3 divided by 2 is 1. And the second one is a system.out.println of 3 modulus 2, which is equal to 1 in this case. Okay, now this is now my new stack. And now, since I am having stack, I will be having 3 calls. I will only be able to access actually the first one. Thus, I will just go and take it. Binary of 1, it's a recursive call. Java will see 1 is not equal to 0, and that's why it will call binary of 1 divided by 2, which is 0. And last but not least, a system.out.println, in this case, of 1. Okay, it's 1 modulus 1. And last but not least, Java will see in the stack 4 calls. However, it sees only the one at the top of the stack. It will go and take it. Binary of 0, it will return. System.out.println of or .print of 1, it will take it and it will print 1 as a result. System.out.print of 1, it will take it and it will print 1 as a result. System.out.print of 0, it will take it and it will print 1 as a result. And this will, 0 as a result. And this will be the result that I will be getting whenever I will call the binary of 6 in this case. Okay, that's if I will do it. Okay, and you do it actually with 6. Okay, the result should be 110, and then actually the result will be 110 in this case. Okay, now let's do it actually in the wrong order. I will take this one, and what I will do is I will just actually convert actually these two statements. Okay, thus I will be having a binary of 6. Okay, now I will do it. It will be put in a stack. The stack actually will consist of only 1. Java will take it and will try to execute it. Binary of 6. 6 is not equal to 0. Okay, and that's why what I will do is I will go to the else statement. You see actually 2 statements. Okay, Java will put them in the stack in the order, and that's why the order is crucial. You will have system.out.print 6 modulus 2 is equal to 0. And the second actually one will be binary of, in this case, 6 divided by 2, which is 3 in this case. Now, please take a look at the stack. Okay, it consists of 2 calls. Java will go and get actually the first one is the system.out.println or print of 0. I will take it and I will actually display the 0 in this case. And then it goes actually to the stack, and the stack is not empty. It will go and take the binary of 3. I will take the binary of 3 and I will execute it. 3 is not equal to 0. I will go to the else part. The else part is consisting of 2 parts. Okay, the first part is first call is system.out.print. It's 3. 3 modulus 2 is 1. Okay, and the second thing is a binary of 3 divided by 2, which is actually 1 in this case. Now in the stack I'm having actually the 2 calls. However, now the system.out.print is the one on top of the stack, and the binary of 1 is at the bottom of the stack. I will go and take actually the call on top of the stack. It's actually 0. What will happen in this case? I will be printing 1 in this case. Okay, binary of 1. I will just take it. It's a recursive call. 1 is not equal to 0. Then I will go to the recursive call for the last time. Okay, and I will be having 2 statements. The first one is system.out.print of n modulus 2. In this case, n modulus 2 will be equal to n modulus 2. It's 1 modulus 2 is 1. And last but not least, I will go to the binary of n divided by 2. 1 divided by 2 is 0. Okay, thus I will be getting 2 calls in the stack. Okay, I will take the one on top of the stack. System.out.println is 0, 1, 1. I'm actually displaying the 1, and then I will be having a binary of 0. Java will not actually stop because I'm still having a call in the stack. I will take it, binary of 0. Okay, now you go and you check 0 is equal to 0. I will return and I will abort from the execution of the method. And now, once I will compile this one, Okay, what you will be getting as a result, if you do it with 6, is the wrong result, because here you will be getting 0, 1, 1, since actually the order is not actually the correct one. And that's why the correct one, just in order to see it actually correctly, is something where you will be having, let's say, the representation done as follows. Now the question is, this is one actually with the void 1, with the void signature. What would have happened if someone want to implement a method that would return actually a string? It is called binary 2 of an integer of x. Okay, now I will tell you this, the following. You have to do it actually in the same way. However, now I will not, let's say, I will not actually have two statements in the else part, but I will concatenate, let's say, the result of the binary 2 in a string in this case. Thus, if x is equal to 0, what I will do is I will just return. Okay, and what I will be returning here is an empty string. Okay, if the x is not equal to 0, what I will do is I will return actually the following. I will return the binary representation of x divided by 2. And last but not least, I will concatenate to it at the end the x modulus 2 in this case. Okay, thus, once we have that, let's take a look at the call itself. Okay, it's public static string binary 2. If x is equal to 0, I will be returning an empty string. Otherwise, I will be returning, let's say, the call of the binary 2 with x divided by 2, concatenated with it the x modulus 2 in this case. Okay, thus, let's go and write actually the following. It's system dot out dot println. Okay, and it's a binary 2 of x in this case. Okay, now let's hope we didn't do any the package still does not exist. Most probably I'm having an additional each end of file. This is this one, int x system. Okay, and you will have a method. Okay, this was the problem. Okay, now we will run it actually with a number. The number is 12. Okay, I should get 1100, and you get actually 1100 if you call it actually with the binary 2. Please here take care. If you do it actually just by reversing the statements, then you will be getting a weird result in this case. Okay, look, what will happen in this case once you will compile and you will run. Okay, if you do it with 12, the result will be in this case 0, 1, 1, because actually it will be done actually backwards, like swapping actually the two statements, binary of n divided by 2 and the system.out.print of n modulus 2. And that's why, okay, what we need actually to do is, okay, we need always to collect the remainder from bottom to top. And that's why this one, okay, should be concatenated. The first one that I get, the first remainder that I will get actually should be the last one, which is actually the x modulus 2 in this case. Okay, thus this one will work. Okay, this is, let's say, in a nutshell, the idea about how recursion works in this case. Okay, 1, 0, 1, 1 corresponds to 8 plus 2 plus 1. Thus, the result actually will be correct. And again, recursive methods are methods that are declarative. And once we have them, it's really easy to, let's say, implement problems in a recursive manner in this case. That's what you have to take from this lecture is the difference between implementing methods iteratively versus implementing methods recursively. That you have always actually to simulate by hand, just to be able to find the mathematical definition of a problem in a recursive way. Writing it down as you saw today is really straightforward. It worked actually for strings, it works for numbers, and in the tutorial you will be getting additional problems. In this case, just actually to know how to distinguish between the implementation of recursive methods and the implementation of iterative methods in this case. Stay safe, stay home. Please try to practice a lot at home. There are a lot of nice platforms where you can actually practice. One of them is Geeks for Geeks. You will find a lot of problems that you can take a look at. You can try them out. Do not actually look at the solutions. Try to solve the problems without looking at the solutions. And at the end of the day, once you face a problem, you can actually just look at how people actually implemented it actually before. If you are having any questions, please send me an email. I will always actually reply to your emails whenever you are having any problem. Thank you very much, and see you next time. Bye.